Okay, so my notation will be, okay. So let's call d sub data is equal to the duration of the data packet. Okay, so I know that in IP, data packets can take different sizes, but for our purposes, let's just suppose that that they're a constant length, and so each data packet contains the same amount of information. Okay, T sub Cn to HA, let's call that the delay from Cn to HA. Okay, Cn and HA are both wired devices attached to the internet, so this will be strictly network latency from Cn to HA. T HA to FAI will be the delay from HA to IF FA. In other words, HA to FA1, that's the delay from the home agent to the FA in the first network. FA2, the second network. So again, HA and FA are both connected to the wired internet, probably. So this is again strictly internet network latency. And finally, T FAI to MN will be the delay from the IFFA to the mobile network. Okay, so to answer your question, Abdullah, I mean these numbers, they're random to some degree, but usually they're pretty stable. This is not network latency. This is strictly the propagation delay through free space. And this will depend on the exact location of the mobile node. But let's assume that we can know it. So let's assume that we have a blocking case where basically an antenna is turned off, and so we're required to switch from one network to the other, but all the distances are fixed. So I think that's a reasonable assumption. Okay, a couple other assumptions. Control packets have 0 duration. There's no computation delay. That's right. And no errors. Oh, one other assumption, all these times are reciprocal. In other words, the time going from A to B, same as the time going from B to A. Okay, so what's this dead time? Well, it's, what is this delay? What's that delay right there? Again? It is, yeah, TFA2 to MN. And this one is the same. And what is this delay?
TFA
to HA to FA2? Yep. Okay, so that's the delay after we change networks. Now the delay before we change networks, that is exactly these two. So that is what? That is T FA1 to MN. this, that there, is THA. I'm going to add one more little segment to this, and actually no, that's fine. That's it. Because I was thinking, okay, you also have to add this, but that's not true. If I happen to have a data packet that arrives right there, the home agent now knows exactly where to forward it, and that's not lost. Okay, so in total, what do I have? I have the delay is given by
you need a delay from CN to HA.
CN to HA. That's what I was just.
Sorry.
That's what I was just saying. So don't need it here because if a packet arrives right there, the foreign agent or the home agent knows where to forward it. And if a packet arrives right there, the home agent knows where to forward it, and it will arrive before the network switches over. So I don't think so. I think I do not need to take that time into account. Yes.
What's the leftmost?
The leftmost T, this one here.
Yes.
That is THA to. Whoops, my bad. That should be THA to FA1. Okay, so what do I have? Let's call it capital T is equal to T HA to FA1 plus T FA1 to MN plus, okay, here these are both TFA2 to MN, so that's 2 T FA2 to MN plus T HA to FA2. And that's the total amount of time that data packets cannot get through. So if data packets are d seconds in length, how many data packets need to be buffered? Any ideas? So I have t seconds of dead time and d seconds per packet. So how many packets? It's t over d, I think. I think it's t over d. So seconds divided by seconds per packet gets packets. It's capital T over D.